In this video we're going to do a short example to show how the rank nullity theorem helps us in calculating kernels and images. So let's begin by thinking about the kernel of a linear map of the form TA. So you'll remember if we have a matrix A which is m by n, and if its entries are from F, and as usual here F represents either the real numbers or the complex numbers, then the linear map TA from F to the n to F to the m is always the left multiplication by A map. So it sends a column vector x of height n to AX, which is a column vector of height m. And the kernel of TA is, by definition, the set of vectors in F to the n such that A times x is the 0 vector in F to the m. So this 0 here is the 0 vector of height m. And of course that is a set of solutions to a matrix equation. The kernel is just the set of solutions to the matrix equation A times x equals 0. So let's look at an example of finding a kernel then. We can use all the methods that we learned in the section of this module on matrices for solving systems of linear equations and put them to work finding kernels for us. So let's say we take my favourite matrix A, which is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 by 3 real matrix. So to find the kernel of TA, what we have to do always is solve the matrix equation AX is the height 3 0 vector. So you can do that by the method of row-reduced echelon form, and especially if this was a more complicated or a larger matrix, you definitely want to do that. So here we form the augmented matrix of that linear system, which looks like this. And then we do row operations, and if you do a sequence of row operations looking for a row-reduced echelon form matrix, what you'll find is the row-reduced echelon form matrix you end up with is this one. So from there we can read off the solutions. If you think of the columns as corresponding to variables x, y, z, then there is no leading entry in the z column, so z can be chosen freely, but there are leading entries in x and y, so x and y are determined uniquely in terms of z. And you find that the solutions are all vectors of the form z minus 2z, z, like this. Or in other words, all vectors of the form z times 1 minus 2, 1. So that's telling you that the vector 1 minus 2, 1 is a basis for the kernel. Every element of the kernel is a scalar multiple of that vector, so that means that vector spans the kernel, and certainly one non-zero vector on its own is always linearly independent. So that vector 1 minus 2, 1 is a basis for the kernel of TA. And we therefore found the dimension of the kernel of TA. The dimension is 1. So let's now think about, in general, what is the image of one of these linear maps TA. So I'm thinking in general, for any matrix A, what can we say about the image of TA? So I claim that the image of TA is always the column space of A, which you will remember is defined to be the span of the columns of the matrix A. The reason for that is if you take any element of the image of TA, it looks like this. It looks like TA applied to a height n column vector, if A is m by n. But you can think of this column vector A1 down to AN as A1 times E1 plus A2 times E2 and so on. Right? I mean, what's going on there is just that A1, A2 is equal to A1 times E1. Remember, E1 means the first standard basis vector, plus A2 times E2, and remember E2 is the second standard basis vector. So that's all that's going on in this equality. We're using the definition of TA and we're just replacing the vector A1 down to AN with the sum of AI times the ith standard basis vector. So because multiplication by A is a linear map, you can move it through the sum like this and get the sum of lowercase ai times A times EI. But A times EI is equal to the ith column of A. This is a standard fact about matrix multiplication. If you multiply a matrix, into the ith standard basis vector, then what you get is the ith column of A. So if we introduce the notation Ci for the ith column of A, then what we've got here is a linear combination of the columns of A. So that shows that every element of the image is an element of the column space. So we've shown that an arbitrary element of the image of TA is equal to a linear combination of the columns, so an element of the column space. Conversely, if you give me any linear combination of the columns, so if you give me, well, some linear combination, sum of AI, Ci, then just reading these equalities backwards, then we can see that that is T of some vector, or TA of some vector, specifically TA of the vector A1 down to AN. And therefore, every linear combination of the columns is an element of the image. So we have both containments, and we've shown the image of TA equals the column space of A. And that's the lemma which I stated right here. Now, the columns of A are not necessarily a basis of the column space. We now know that they are a spanning sequence for the column space, but they're not necessarily a basis, because they might not be linearly independent. But what we do know from lecture 39 or video 39 is how to find a basis of a span of column vectors. We developed a method for doing that in that video. So we could, in principle, whenever we want to know a basis for the image of one of these maps of the form TA, we could apply the method of lecture 39 to find a basis for the column space of that matrix A, and that will give us a basis for the image of TA, because the image of TA is the column space. But sometimes we can avoid doing that, and here's an example of where we can avoid it using what we know from the rank nullity theorem. So I'm returning to the same example at the start. A is the 3x3 matrix, which I've written here, and we know from the last slide that the image of TA is the span of the columns of A, the column space of A. So this here is the column space. And let's say we want a basis of the image of TA. But what it helps us to know is the dimension of the image of TA. And because we already worked out the kernel, and because we know that A is a 3x3 matrix, we can work out the dimension of the image without doing any work at all. Because the rank nullity theorem says that the dimension of the kernel of our TA, which is 1, plus the dimension of the image of TA, which we don't know but we'd like to know, is equal to the dimension of the domain of TA. And because A is a 3x3 matrix, that domain is R cubed, so its dimension is 3. Okay, 1 plus the rank of A, or the rank of TA, is 3. So this dimension of the image of TA, the rank of TA, is 3 minus 1, which is 2. So we know, whatever this image is, we know that its dimension is 2. So even if we didn't know this, even before we knew the rank nullity theorem, we could have gone through the procedure from video 39 to find a basis for the image of TA, for the column space of A. But now we know the dimension is 2. We could simply observe that any two linearly independent vectors in the image of TA must be a basis. Because if you take any two linearly independent vectors, let's give them names. Let's suppose we happen to find somehow, one way or another, two linearly independent vectors, x and y, in the image of TA. And if they're linearly independent, then their span of x and y would have dimension 2. So their span would be a subspace of the image of TA, whose dimension was the same as the dimension of the image of TA. And we know that if you've got a subspace of a vector space, and the subspace and the big vector space have the same dimension, then actually the subspace is the whole of the thing it was a subspace of. So if you can find any two linearly independent vectors in a two-dimensional vector space, then their span is the whole of the vector space. So they're a spanning sequence, they're linearly independent, and therefore they're a basis. So this argument is very, very useful. We use it all the time. If you can find n linearly independent vectors inside an n-dimensional vector space, then they must be a spanning sequence, and so they must be a basis. So here, if we can just somehow spot two of those vectors which span the image and which are linearly independent, if we can spot amongst those vectors two linearly independent vectors, then those linearly independent vectors must be a basis for the image. And actually it's very easy to check that these two vectors are linearly independent. If they weren't linearly independent, one of them would be a scalar multiple of the other, and it's very easy to show that's not the case. There's no scalar which you can multiply the second one by to get the first, or multiply the first one by to get the second. And therefore they're linearly independent, therefore they are a basis of the image of TA. So the rank nullity theorem very often gives us information which we can use to make calculations of bases of kernels and images easier.